Okay.
All right, so here, this was our expression for angular momentum before that we used, L equals I omega. And I wanted to look at another form for the angular momentum expression if we're dealing with point masses. So for a point mass that's at some distance r away, we can write the moment of inertia as just mr squared for a point mass times omega, we can just write as v over r. That gives us mvr for an equivalent expression for the angular momentum. Now notice here that this is a linear momentum, here, mv multiplied by a radius. And so that's true, but it's only true in general if the mass is moving perpendicular to the radius vector. So it turns out that a more general form that involves point masses is going to be a vector cross product. And it's going to look like r cross mv, or r cross p. So a vector cross product then is something that we've kind of implicitly already been doing with torque. For torque, this is just equal to r cross f. That's a vector cross product of a radius vector and a force. Okay, and so the magnitude of the torque we saw before was equal to rf times the sine of theta. Same thing is true here. This is our general property for a vector cross product, is that this is going to be equal to the magnitude of r times the magnitude of our linear momentum, mv, times the sine of theta, where theta is the angle between r and v. Whereas here, theta is the angle between r and f. Now, to do that, but that just gives us the magnitude. Okay, so the magnitude of L, then, I should say here, is going to be equal to the magnitude of r cross mv, magnitude of r times the magnitude of mv times the sine of theta. Okay, so that's true then for the magnitude. How do you get the direction? Okay, well, the way that you get the direction is by doing what we call a right-hand rule vector cross product. And so the rules then for, let's just say in general this is C is equal to A cross B. We want the direction of C. Okay, so first of all, the direction of C, which is the vector cross product of two vectors, if you know nothing else and you forget everything else that I tell you, you know that it's going to be perpendicular to the plane that's defined by A and B. So if I have two vectors, let's say A and B, I'm going to need to put their tails together. It's okay to do that with vectors in general, because they just have a magnitude and a direction. So you can move them around anywhere you want. So this is just a convenient place to put them. And then theta is the angle between A and B. That's the magnitude of C. It's equal to that. Okay. And so we put the two tails together. That's step one. Step two, here, pay close attention to this. You stick your right arm in the direction of V. And you curl your fingers in the direction, in the direction of A. and then curl your fingers in the direction of B. So the first one is the one you stick your arm in the direction of here. That's going to be A. And then I'm going to curl my fingers. Just imagine that the A vector is from my wrist on out, and the B vector is the pin from my wrist out. Then I'm going to curl my fingers in the direction of B, and then, unless you're a contortionist, there's only one way your thumb can point. And so in this case, it's into the board. Then just look at the direction of your thumb. That's going to curl in the C direction. Okay, so for this problem then, A cross B is going to be C. So C then is into the board. So that's our general procedure then for getting the direction of A cross B. Where A and B are just two arbitrary vectors. Now, in this class, we're going to have some situations where we need to do that. In 2.8b, you're going to have a ton of them where you need to do that. So this is really important that we get this going now, so that even though it's not super critical for what we're doing in 2.8a, you're ready to go when you get to 2.8b. All right, so with a torque problem then, and we'll have more applications of how to use this when we get to the gyroscope soon. With our torque, let's say that we have a wrench and then we apply a force, let's say like this, through this radius vector r. Then I can put r and f together, and we see here that it's r cross f is the direction of the torque. Okay, so then this is going to be stick our arm in the direction of r, curl our fingers in the direction of f, and that'll give us a torque that's out of the board. So we can think of this as kind of like an axis for the torque. This is the direction in which the torque is being delivered. Okay? And so if we go round and round like this, and we're unscrewing a bolt by applying a force at some angle theta, now if we were smart, we'd be applying it at a 90-degree angle here. Otherwise, we're wasting some of our energy. Right? And also the other problem here with this open-end wrench, applying a force like this, some of the compound is going to pull the bolt right off the wrench. So if I were really going to have a realistic function here, it would probably be one in which this is a box end wrench. Okay, and then you twist it this way. Notice though that when I curl my fingers in the direction that the object's going, that also gives me the same direction for the torque. And this is also true of the angular momentum. If I've got something that is moving like this, v, this is r, and then I go r cross mv, like this, then the direction of this rotational axis is going to be out of the board. And so that is the same thing that happens if this thing is going round and round in a circle, and you're just curling your fingers around in the direction that it's going. So for an object that's rolling in a certain direction, you can get the direction of the rotational axis just by kind of curling your fingers around the object and then seeing which direction your thumb points. But this is the more general approach, and this is something that you really do need to get used to, especially for 2AP. So here's an example. of how this would work. We could say then, well, what's the direction for the angular momentum that's associated with the Earth? And we, of course, know the Earth is rotating counterclockwise, like this. So if I go around like this, notice the rotational axis is through the south and the north and up like this. So the direction of the north axis is the direction of omega, and also the direction of my angular momentum for the Earth. Remember, L equals I omega. So omega points in the same direction as L, but that points in the same direction as R cross mv. Okay, and so we'll be using that as we do these different kinds of problems. Now, so far, we've only looked at problems that involve L equals I omega. I want to look at another example of one that deals with a point mass. Let's say that we have a bullet, and that bullet is moving toward a mass. And that mass is a big block that is hanging from a string, like this. So here comes our mass in like this. Here's little m. Here's some velocity v naught. We might be interested, once we choose a pivot point, in finding the angular momentum of the bullet about this pivot point. You might say, well, why on earth would I want to do that about that pivot point? I could do it about any other pivot point too. The answer is because this mass is going to hit this one, it's going to embed into it, and this is going to cause the system to go up to a higher state of potential energy. So we've already done this problem. But what I want to do is reframe this in terms of angular momentum, the same exact problem in terms of angular momentum. So how to do this? Well, we can use conservation of angular momentum if we can figure out the angular momentum of the mass at this distance r away. So here's our r value, r. Okay, and so if we want to figure out the direction of this angular momentum, this is r, and this is mv, then we do r cross mv. That would give us a direction of L that's out of the board. And so then, this would be the angle between R and MV. Now, when it gets over to this point, if it didn't hit that block, let's just say it goes on its own. Let's take the block out of it for a second. Let's say it's over here. You could also figure out the angular momentum here. Some distance R away. This would be MV. And at this point, it would be R, this would be MV. So it would be R cross MV, and this would be the angle theta. So R cross MV comes out of the board. Here we've got R cross MV still coming out of the board. This times the sine of this angle. Okay, now the sine of a really big angle like that, that's more than 90 degrees, is still positive, because all students take calculus. Okay? So the sine function, if this is, say, in the first quadrant, then this is in the second quadrant, or you could say that they're both negative if you wanted to, but if we just define our axis to be down, then this would be, let's say, if it's at equal distance on the other side, then this angle could be the same as that angle. And the angular momentum would be the same, because the sine, let's say, of 30 is going to equal the sine of 150. So in other words, this angle could be 150, If it's an equal distance on the other side, this would be 30. So it would be the same in either case. And so what is that equal to in general then? Well, it's equal to the magnitude of L is the magnitude of the mass times the magnitude of the velocity times r times the sine of theta. And so that's our expression for the angular momentum in general. But r sine theta is just this distance. And now what is that here? Well, r sine theta is the same as this distance here, which I could call L, regardless of what theta is. Whether it's 30 and 150 or whether it is 160, then this r is going to be bigger, but the r sine theta will always be the same, regardless of theta. Be way out here too. Then this would be a different r times the sine of theta, but that r sine theta is always going to be the same value for L. Or we call this little l here because I don't want to confuse that with angular momentum. Okay, so what that tells us then is that the angular momentum is the same about this pivot point, any point along this line. The angular momentum is the same. Always along that line. And so that means the angular momentum is constant. So that's conservation of angular momentum about some pivot point that we've chosen there. L before equals L after because it hasn't had anywhere for the angular momentum to go. Okay, and so we can say then that L, now let's put this thing in here and say that there is a collision, like we had in the ballistic pendulum. Then let's find L just after the collision. How do we do that? Well, we have L before now. L before is just equal to mvr sine theta, but that's just equal to mvl. Why? Because L, this distance here, is always r sine theta. So that means that regardless of where the bullet is along its path, whether it, and if it didn't hit something, it would still be the same way out there. But now its angular momentum is going to be injected into this larger system. And because of conservation of angular momentum, we can say then that L initial equals L final. Why can we say that? Well, because there's no torques acting on the system from the outside. There are torques acting within the system. This mass is slowing down. So it's changing the angular momentum of the bullet to a smaller value, and the bullet is speeding up or increasing the angular momentum of the block. But the two of them together aren't being acted on by some external torque from the outside universe. Okay, so we could say here then that little mvl equals, and then just after the collision, this is going to have some final angular velocity omega final. Okay, so we can write this then as I final omega final, okay, where I final is just equal to little m plus big M times L squared, because this is a point mass at a distance L away from the pivot point. And so now we see why we chose this pivot point, because this thing is going to start to swing about that pivot point. So we want the angular momentum of this component to be consistent with our definition for the angular momentum of this mass as it's moving in to strike it. Okay, so MVL then equals I final omega final, and so little MVL is equal to little m plus big M times L squared times omega final and so that means that we can solve for omega final. This is our angular velocity just after the collision, and that's going to be equal to little m divided by little m plus big M times and then one factor of L is going to cancel, so this is going to be times L. And then this is going to be times V there. Okay, and so that's going to be the final angular velocity of the system after the collision. Then what we can do at this point is say that, well, is that consistent then with a final velocity in the ballistic pendulum where the final velocity just after the collision divided by L is equal to omega final? Well, then if I plug in V over L is equal to little mv divided by little m plus big M times L, then the L's cancel, and that gives me big V is equal to little m divided by little m plus big M times V naught. And this is the same result as we got using conservation of linear momentum. During the collision in the ballistic pendulum. Okay, so you might say then, well, then why do we go to all the trouble of writing this in terms of angular momentum when we could have just done the whole thing with linear momentum? The answer is because I used a simple example. Okay? What if I used a more complicated example like this one, in which now instead of having a mass, what I've got is a uniform stick of length L that's hanging from here. And then this bullet comes in and hits at the bottom of the stick. Can I solve that one using conservation of linear momentum? Answer is no, because the stick is going to have a moment of inertia about this pivot point. Okay, and so even though I was able to show here that I get the same result when it's using point masses, let's try it now with the stick. Okay, so with the stick then, what we've got, if the length of the stick is L, instead of being the length of the mass, let's rework this for the stick. The bullet is fired into the bottom of it. Like this. Then what's my omega final going to be equal to? Well, it's going to look just like this equation, but with a moment of inertia of the mass rotated about its edge. So this would be I final be 1/12 little m, big M. M is the mass of the meter stick. times L squared plus little m times L squared. Because we have a point mass at the end that has a mass little m, and we've got a longer stick that has a mass big M and a length big L. So this is going to be I times omega final. So now we can figure out the final omega for this problem. It's going to be a little more complicated. Omega final then will equal little m, call this V naught for the initial velocity of the bullet before it hits the meter stick, divided by 1/12 big M, which is the mass of the meter stick, or whatever stick it is, times L squared, which is the length of whatever that thing is, plus little m L squared. Okay, so we can pull out a factor of L in the numerator and denominator. That would give us little mass times little velocity divided by 1/12 m plus little m times L. That would be the final angular velocity just after the collision. Now, we're going to lose energy during this collision, but we don't lose angular momentum. Just the same way as in a linear problem, we don't lose linear momentum. Even if rotational energy or whatever other kind of energy you have in the problem is lost in a problem like this, we don't lose angular momentum. So once we have the angular momentum, then we can use conservation of energy. To find how far it swings up. Okay, so it starts out with an initial, which I'm calling the final from the previous problem, but now our initial kinetic energy at the bottom is going to be equal to 1/2 I omega final. I'm just using the final from this notation here, but it's actually the initial I for the second part of the problem, which is the swing, as it swings up to some height. And then to figure out the height, what we would need, if this is, say, when it's in this position, if this is the potential energy, then we'd need the center of mass of the system to see how high up it goes. And so the final PE would be equal to little m plus big M times G times delta HCM. So this is a little tricky because the center of mass of the meter stick moves a different amount vertically than the mass does. But if we looked at the center of mass between those two, let's say it was at this point here, then you could call this the zero reference position for potential energy, and this the final reference position, and then this would be delta HCM. And so you could just set the kinetic energy equal to the potential energy final, and then you could find the height that the center of mass has risen. Once you have the height that the center of mass has risen, you could figure out anything else from the problem using geometry to figure out, for example, how far the mass itself rose, or how fast the center of the meter stick rose. Okay, and so this gets us into a realm of problems that are a little more complicated than some of the other ones we've looked at. And if you think this one is complicated, wait till you see our next lecture on gyroscopes.